Welcome to Tikal's meetup on agentic systems that remember memory, context, and architecture. My name is Rivka Spiegel, and for the past 5 years, I've been a backend engineer and architect here at Tikal. But my journey into technology started long before that. I was born and raised in New York, and at university I studied computer science, mathematics, and economics. I specialized in Java and had one goal: to work on Wall Street and to have a beeper. I got my first job at Lehman Brothers in the Twin Towers 3 months before September 11th. I started with Visual Basic, Oracle, and what was then an exciting new technology, XML. Then 2008 happened, Lehman Brothers collapsed, and I had to reinvent myself. My next stop was Progressive Insurance, where I dove into C#, ASP.NET, and the Microsoft ecosystem. The next turning point was outside of work. My husband and I had promised ourselves that after 10 years together, we'd move to Israel no matter what, and that's what we did. After making Aliyah, I eventually joined Mobile ODT. It's a company that fights cervical cancer in low resource settings. And once again, everything changed. Working alongside Tikal consultants, I experienced several major architectural shifts, from monoliths to microservices, then to event-driven systems, and finally to serverless architectures with Node.js and AWS Lambda. When COVID hit, funding shifted and I had to pivot once again. That brought me to Tikal, where my first client, 1.0, introduced me to Kotlin and Snowflake. Missing event-driven systems, I moved to Yotpo to work with Kafka and OpenSearch at scale. And today, I'm at Big Panda, working in yet another paradigm: Python, data pipelines, DLT Hub, and Apache Flink. Technology will continue to change, and so will we. That's both the challenge and the privilege of being an engineer. If you decide to be an engineer, you're basically a student for life. Today, we're living through another one of these shifts. This one is agents. Like many others, I've been overwhelmed by agents, agentic systems, and their architectures around them. The space is moving fast, and it's difficult to make sense of it all. To get oriented, we'll cover 3 things: how agents became practical, agent architectures, and the framework landscape. So let's step back for a moment and understand how we got here. In the 1950s, Alan Turing changed the entire discussion around AI. Before Turing, we tried to replicate human reasoning step by step in a machine. After Turing, the goal became producing intelligent behavior regardless of how the machine worked. If a machine could fool a person into thinking that it was a human, that was AI. When intelligence is defined by behavior, the rational agent model explains what an intelligent system does. It perceives its environment, decides, and acts to achieve a goal. This simple loop became the foundation for decades of agent research. Early agents were built around the idea of rational, goal-directed behavior. They assumed the agent could model the world, plan ahead, and choose the optimal action. That approach only worked in small, predictable environments and broke down as soon as the world became complex. Notice this started in the 1950s. We have been running after this goal for 75 years. Expert systems followed, trying to capture human expertise with if-then rules. It worked until the rule set exploded. Reactive agents use simple perception-action loops, enabling fast responses. But without planning or memory, they couldn't pursue goals over time. Multi-agent systems explored coordination between many agents, but the systems were hard to engineer, predict, and control at scale. Reinforcement learning reframed agents as learners that improved through reward, but the approach required massive data and stayed domain-specific. Software agents proved autonomy at scale in production systems, but they were narrow, scripted, and not truly adaptive. The best example of this is autoscaling. If we go with the model of proceed, decide, and act, if you perceive the CPU in your system and you see that it's too low and you need more, then you add a pod. If you see that there's too much and you don't need as much, you remove it. So again, perceive, decide, act. Up to this point, agents could perceive and act, but the way they decided was fixed in advance, creating a hard limit they couldn't push past. That pattern broke with large language models. For the first time, goals, tools, memory, constraints, reasoning, and even plans could all be represented in the same medium, language. That meant we no longer had to program every decision. We could describe the objective, provide the capabilities, and let the model determine the next action. That shift didn't just change how we write code. It introduced a new building block, the agent. Just like the database is a building block, and your load balancer is a building block, and your language is a building block, you now have a building block called an agent. An AI agent is a component, often backed by an AI model, that receives a prompt, makes a bounded decision while optionally invoking tools, and returns an answer within a single request-response cycle. An agent is more than a prompt and a response. It must decide how to act. Agentic systems emerge when solving the problem outgrows what a single agent can reliably handle in one interaction. In agentic systems, the model can plan, act, observe, and refine its behavior. Past context and outcomes inform future decisions. Behavior adapts based on results and feedback. And the system operates over time, not just within a single interaction. Once systems look like this, architecture is no longer optional. Everything up until now was about how we got here. From this point on, we're talking about design choices. We'll review insights from the Ultimate Guide to AI Agent Architectures by Sohail Akbar. We'll cover 8 agent architectures, 4 in depth and 4 at high level. For each deep dive, we'll cover pattern, flow, use cases, rationale, limitations, and key takeaways. So normally I like a lot of images, but in the next set, we're going to have a lot more bullet points. Because just like if you choose your database, you have to worry about things like CAP, consistency, availability, and partitions, or what you're using your database for. Do you need it for quick updates? Do you need it for analytics? These are the same concepts that you have to, those are the concepts for databases, and here you'll have a new set of concepts that you have to think of when you're going through your decision of what type of agent architecture you need. Okay, so starting simple, single agents and tools. The single agent and tools architecture consists of one autonomous AI agent leveraging multiple external tools to accomplish tasks. In the control flow, the agent receives the task, reasons about the next step, selects tools and input parameters, executes the tools, observes the results, and repeats until done. This pattern is commonly known as react, reason, and act. This agent architecture typically includes a language model for reasoning and decision-making, clearly defined tools it can call, a memory system to retain history and intermediate results, control logic to orchestrate the decision-action loop, an execution environment to safely run tools and external actions. This architecture works best when one agent has one objective and can use whatever tools it needs to get there, when gathering data from different sources that is then combined into a useful answer, and for systems handling everyday tasks like emails, calendars, reminders, and bookings. So again, in the beginning I said we're basically trying to reproduce human behavior. So a single agent is like a single programmer. When we have a small task, you don't need 10 programmers, you need a single programmer, or you need a single agent who has the correct tools. Teams choose this architecture because it's simple to reason about, easy to debug, has predictable failure modes, and is about 50% cheaper than the more complex agent architectures with comparable accuracy. Limitations include a single agent must manage everything within one context window. The more tools you add, the more performance decreases. Mistakes in early reasoning cascade through the solution process. Tasks that require complex multi-step planning perform weakly, and the results are not consistent across retries. Again, if you have one programmer working and you give them millions of tools that they have to be the ones that are experts on, they're not going to perform as well as if you can divide it between more than one programmer. Also, if it's one programmer and they make a mistake in the beginning, it's going to go all the way through, opposed to if you have more than one and they can have a discussion. Same behaviors, just moving it to agents. When planning, memory, or coordination grows, a single decision maker becomes a bottleneck. Single agent plus tools and router. To reduce the bottleneck in our next model, decision-making was constrained to predefined choices. Here, a single agent selects one predefined path or tool based on the inputs, rather than reasoning through multiple steps. In the control flow, user provides the inputs, router determines the appropriate path or tool, selected tool is executed, and the result is returned to the user. The agent makes one decision per interaction. The core components include an LLM serving as a core reasoning engine, external functions, APIs, or capabilities that the agent can invoke, and a mechanism allowing the LLM to select a single step from specified options. This architecture works best when sending requests to the right team or service. My password needs to be reset. Do I send it to HR? Do I send it to IT? When choosing the right source of information, am I going to the company knowledge base or am I going to the web? When sending different types of requests to the right system, if it's a sales request, send it to Salesforce. If it's an IT request, send it to ServiceNow. And finally, when writing requests to the correct application or microservice, where's my order? Do I have to look in sales or billing or shipping? This is the classic chatbot, right? It used to be when you had the chatbot, you had to say, like, you sat with the UX person, you asked the UX person, okay, these are the buttons they press. If they press button 1, then these are the next screen, or 2 and the next set of screens. You had to hard code the decision section. Now, the LLM can understand from just the message where it should go, but it's not going to be able to go to infinite amounts of places. It still is only making a very small decision to a small set of places. Teams choose this architecture because routing improves accuracy in well-defined domains, which leads to higher task success. By narrowing decision space, it reduces latency and produces more consistent tool selection. The architecture struggles with ambiguous queries that don't fit predefined categories. Right? If you're going to ask me about shipping or about orders, but if I'm an ordering system and you ask me about the weather, I don't know what to do. It has no flexibility beyond the predefined paths. And the context handoff between tools is fragile. Accuracy degrades as routes increase, and it has poor multi-step reasoning. Routing works when intent is clear. It breaks when the system must think through a problem. Single agent and dynamically call other agents. In our next architecture, instead of fixed paths, a single agent stays in control and dynamically invokes specialized agents as needed. This is one of my favorite because it's so like human behavior. Fridays, I'm very busy. I get up at 6, I work until Shabbos. I have tons to do. I have 4 big kids. I would get annoyed if they sat in bed and I had to do everything. I have 4 bathrooms. I've decided Friday, I'm delegating the bathrooms to them. Again, same thing here. You have to decide, the agent has to decide when it should do its work and when it's best to give it to someone else. In this control flow, a primary agent receives a request. The primary agent reasons about the task and decides whether to handle it or delegate. If the primary agent calls a specialized agent, the specialized agent executes its task and returns results to the primary agent, who then integrates results and continues. Delegation is a choice, not a fixed workflow. Core components include, again, a central orchestrator for reasoning, control, and synthesis, task-specific agents performing particular functions, an orchestration layer that manages communication and state, logic for determining which specialized agent to invoke. This architecture works well when requests span multiple expertise domains, when managing complex workflows with specialized handling, when specialized agents are expensive and should only be invoked when necessary, and when a general agent handles basic inquiries but routes complex topics. In a company, this is a classic, I was a one programmer company, it's getting too much for me. Do I go for a junior programmer who I can then delegate all the things I already know how to do and keep just the more important stuff? Do I go for 2 senior programmers? The same concept here. When do you delegate and when do you do the work by yourself? When properly designed, routing improves overall accuracy. It introduces small routing delay, but often saves time by engaging the right specialist immediately. It reduces token usage compared to a single large agent approach and has a higher task completion rate. There are several technical limitations to consider. Primary agent must make accurate decisions about when to delegate. If your team lead decides to do it all himself and not give it to everyone and therefore doesn't make the deadline, that's a problem. Context handoffs are complex. Additional complexity in managing state and communication. Different agents may have distinct response styles. This is the classic, I don't know how many companies I've been in that have tried to make the JIRA format the same or the PR format the same. You have to have the PR to the JIRA, you have to say what the issue was and the task is. Same exact thing. Everyone is trying to make the response style the same so agents can better interact with each other. And initial routing decisions aren't always optimal. Again, if you chose the wrong thing at the beginning, your whole flow is busted. As delegation increases, reasoning about the system becomes harder than reasoning within an agent. Obviously, if a project is one agent, it's easier just to deal with that one agent. Project is two agents, then you have to figure out how to properly divide the work. Agent hierarchy, loop, and parallel agents, and shared RAG. A bit of a mouthful. In this architecture, a hierarchical multi-agent system where agents work in parallel, refine results through loops, and share knowledge by a common retrieval system. This is a case where you have a feature that crosses multiple groups within your company. In this control flow, a supervisor decomposes a task. The subtasks are delegated to the agent hierarchy where agents run in parallel. A RAG provides common knowledge. Feedback loops refine partial results. And finally, results are aggregated and synthesized. Controls flows vertically, work flows horizontally. Here, the RAG is that requirement doc. The requirement doc that you spend weeks on and everyone updates it, and then finally all the stakeholders have to say, okay, we all agree on that, right? So if somebody changes something, we know who to speak to. This is the same thing. The RAG is supposed to be your master requirements doc. Core components include multiple forms of expertise, iterations and refinement, multiple agents working simultaneously, central knowledge store accessible to all agents, and standardized messaging system. The architecture works well for large-scale research, multi-stage content creation, cross-domain problem solving, and complex data pipelines. Teams choose it because it demonstrates faster completion of complex tasks, higher output quality for tasks requiring diverse expertise, stronger knowledge reuse across agents, better adaptation to changing requirements, and lower error rates. Just to go back to the faster task completion, right? When you're dealing with humans, if you always chose the expert, the guy who would do it fastest to finish a task, your programmer will leave soon because nobody wants to do the same thing over and over and over again, right? So usually you have to take a hit on speed in order to give the senior programmers something more interesting to do and the junior programmers to step up. Agents, nobody's going to say to you, I've done this 100 times, I don't want to do it the 101st time. The benefit of moving to the agent. The challenges with architecture include very high complexity, coordination overhead dominates simple tasks, parallel agents accessing shared resources require concurrency control, increased compute costs, and debugging is significantly harder. Again, if you have multiple programmers on a project and there's a bug, you got to go through all of them to figure out what your bug is. And even if I knew the bug is not with me, I'm going to spend extra time proving it's not with me before I go after a different programmer and say, oh no, the bug is with you. Another thing here is that coordination, the one that said coordination overhead. In the end, when I go through a framework, I made the wrong decision. I chose advanced framework in order to deal with a simple task. And the coordination, we'll see, is what killed me. So you have to think, do you really want to introduce complex coordination if the task really just needs one agent? This architecture optimizes for capability, not simplicity. Okay, so these are the next four. They're very similar to the first, but it's pays just to know them. So sequential agents, the work is split across multiple specialized agents that operate in a fixed sequence. This is the default when you don't need routing or parallelism. If you get to a point where you just can't give your agent more tools. We said it before, if an agent gets too many tools, it doesn't work as well. So then you have to introduce another agent, but you're really just doing it for its expertise, and you need all the complicated communication back and forth. The single agent and MCP server uses tools exposed through standardized servers rather than integrating with each tool directly. MCP solves integration, not planning, coordination, or autonomy. We constantly say an agent is someone with tools. When you had to integrate each tool individually, it was hard to give them the right tools. Once you had a standard, it's easier to make your agents have the tools that it actually needs. Our third architecture, supervisor agent, delegates work to specialized agents that execute tasks in parallel using shared tools. Here, reasoning is distributed, control is centralized. So here, basically, you just have to divide the tasks and run in parallel. There's no coming back to each other or having to coordinate with each other. The last one, a single agent performs routine work but pauses for human judgment at predefined decision points. This architecture optimizes for correctness, not speed or scale. Here I kind of think about it as a senior programmer and their junior programmer. In the beginning, you're going to be on top of your junior programmer. You're going to want to know how he's doing his work. You're going to want to follow its tasks. Just like if I ask cursor now, build me the plan, but do task one at a time, I want to see everything. But as I train my agent or my junior programmer to do things in the style that I like, then I stop stepping back. I'm not micromanaging anymore. The same thing with the agents. We don't want to really be, especially when you're programming, to be human in the loop. You want to get to the point where you've taught your agent to do more work on its own, to free yourself up to do other things. As you can see, there's no best agent architecture. Each team simply needs to choose the best solution for their situation. Just like there's no best database, no best load balancer, there's no best event-driven technology. Agent architecture is just a new building block. Just think of the same processes you did when you choose databases. Think about similar things when you're choosing agents. Up until now, we've been talking about how different agent architectures behave and the trade-offs they introduce. As these systems become more sophisticated, managing them becomes increasingly complex. That's where frameworks come in. They help manage that complexity. At a high level, most agent frameworks provide the same core building blocks. They define how agents interact with users, systems, and each other. They manage memory and context, connect to language models for reasoning, integrate tools that let agents take action, orchestrate workflows across one or many agents, and provide connectors to existing platforms and services. The differences aren't what they provide, they're how they implement those capabilities. As part of our last topic, we will explore LangChain, LangGraph, AG2 AutoGen, Crew AI, Pydantic AI, and Agency Swarm. These are just a few of the many that exist. Okay. 3 years ago, when LangChain started, Harrison Chase understood two things. LLMs were powerful, building reliable agents was hard. That insight shaped the next 3 years with one goal: to figure out what the agents of the future look like and build the tools to make them real. LangChain started as a side project born out of early LLM experimentation. As more developers built with LLMs, the same pattern kept emerging. LangChain turned them into reusable building blocks, making it easy to go from idea to application. It used to be, if you wanted to run a select star from given table where ID is Y, you had to write a piece of code that said, open the connection, define the statement, get the result, close the statement, close the connection. Now all you do is object.findMe by ID. The same concept here. All of the boilerplate that kept on coming up, they templated it so that you can now just say, give me the LLM and give it the credentials instead of whatever you had to do before to actually connect to the LLMs and all the things underneath. As LangChain moved into production, control became unavoidable. LangGraph makes agent behavior explicit and provides a production-ready runtime. In a nutshell, LangChain defines agents logic using modular components, and LangGraph executes agents with explicit control and production guarantees. Together, LangChain and LangGraph provide the building blocks and orchestration needed to create production-ready agents. Okay, so take this short program in LangChain. In a nutshell, it takes a common chat pattern and turns into a simple, reusable flow you can build in minutes. I set the max history to 5, so it'll lose the context after 5 exchanges. Let's see in action. And also, it's a good way for you to see how Amit answers the question, because I'm going to lose the context in 5. Okay. So, I went with like the classic hello world type of thing, right? So, hello, how are you? And the agent says, I'm a bot. And then I'm going to ask it, what color is the sky? And this is round 2. And it's going to tell me something ridiculous. And what color is a rose? Again, so we're up to, 1, 2, 3. And then we're going to say, what did I ask you about the sky? Still knows. Ask it something else to get past the 5. What color is a tulip? And I'm going to ask again about the sky. And it's gone. Okay, but it was really simple to do it, but it only keeps it for 5. Okay, so I implemented the same chat example with LangGraph. Instead of a linear loop, the conversation is modeled as a graph with explicit state and routing. Each user message goes through the router node that decides what happens next. It's the same idea with much more control. Here, watch what happens when I ask about roses. Okay, so again, I did the same thing. We're going to start with a hello. And then I'm going to ask about the sky. And then I'm going to ask the color of a rose. And now you'll really see that I'm American. Roses are red, violets are blue, sugar sweet, and so are you. It's very American. We learn it when we're in kindergarten. What did I ask about the sky? You asked what color is the sky. Great, it still kept the context. What color is a tulip? Okay, now I asked the same question about a rose, but a little differently. Again, roses are red, violets are blue, sugar is sweet, and so are you. What I asked about the sky, we're past 5. I don't know anything anymore. Okay, so I mentioned before, so in LangGraph you define nodes, and here the LLM had to make a decision that if there was the word rose in any of the messages, then it went here and it always answered roses are red, violets are blue, sugar is sweet, and so are you. I personally used LangChain and LangGraph in 2 hackathons. At Tikal, we won 1st place. At Big Panda, we won 4th place. This past year in Tikal's hackathon, I also had to do a presentation of multi-agents. Again, I went back to LangGraph. The environment really delivers on its quick onboarding. Okay, next. Microsoft AutoML research focused on automating the machine learning pipeline. As LLM applications became more complex, that work evolved into AutoGen, a framework for coordinating multiple AI agents. One of the first ideas AutoGen introduced was a user proxy agent. Rather than asking the language model to imagine running code or using a tool, it created a dedicated agent whose job it is to act on the user's behalf, executing code, calling tools, and bringing the results back into the conversation. The real breakthrough, though, was realizing that conversation itself is a powerful mechanism for reasoning and coordination. Instead of rigid control flow, AutoGen embraced multi-agent conversations to structure complex problem solving through dialogue. How many times have we been told that one of the best reasons to come back to the office is those conversations in the hallway or around coffee? Same thing here. Having a conversation will lead to ideas that you wouldn't have if you're just at home doing it by yourself. When working with this framework, the best practices include starting with a reasoning agent and user proxy agents. Add more agents only when needed. Not big chachma. I start an Apache Flink cluster, start with 3. If I need more, I'll add the 4th KPU. Same ideas. Break complex tasks into specialized agent roles. Choose the right communication pattern, sequential, group chat, hierarchical, and way. Match the model to the task, not to the price tag. Interesting that he focused on breaking complex tasks down. When I used to interview junior developers, one of the things I would do is give them a task, not ask them to code it, but ask them how would they break it down into smaller pieces so that it's easier to test, easier to release. The idea of being able to break down complex tasks for agents is crucial. It makes it a better agent if it knows what it's doing. In this snippet, I define conversational agents who are sports analysts. For fun, I asked Cursor to add the ability to speak the conversation that was generated. Since I had to do all of them, I decided to have a little fun. So again, I created 2 agents. I know more now than I did then. I probably would have given them better messages, but this is what it produced.
The rivalry between Magic Johnson and Larry Bird.
Magic and Bird's rivalry transcended basketball, revitalizing the NBA and establishing a cultural phenomenon that still resonates today.
Their contrasting styles, Magic's flashy playmaking against Bird's lethal shooting, defined an era and showcased the game's diverse talents.
Their battles on the court not only defined the 1980s but also laid the groundwork for the league's modern global appeal.
The personal rivalry fueled an intense competitiveness that captivated fans and increased viewership, revolutionizing sports marketing.
Their dynamic pushed both players to elevate their games, creating unforgettable moments that turned basketball into a primetime spectacle.
Okay, and very American, I chose basketball. I think if I was Israeli, I would have chosen soccer. But just like I lived through many different technology events, I also got to live through Magic Johnson and Larry Bird, Jordan and Pippen, and LeBron James. So even though I don't like basketball, it's fascinating the human behavior you get out of sports, just like in agents. AutoGen isn't about building bigger events, it's about building better systems. Okay, the next one is very interesting, and it was actually the easiest to deal with. Like many good ideas, Crew AI started with a nudge from someone's wife. Joe Moore's wife wanted him to post more about the cool things he was doing with AI. So he began by automating his own posts on LinkedIn and X. And that small experiment grew into a mission to make AI accessible to everyone. He basically taught his AI a little bit about himself, gave him anecdotes, stories from his childhood, then gave it a topic and said, like, go write it, but make it personal. And it was extremely successful. Crew AI focuses on building autonomous AI agents that collaborate as a crew, where agents are defined by roles and work is defined by tasks. Through clear task ownership, coordination, and communication, teams of agents can reliably solve complex problems. Often when you have multiple programmers, you have this issue. Where does their job end and where does your job begin? That issue with behavior of programmers, he tried to avoid in agents. Give them clear roles, clear tasks, they'll work better. Crew AI is built around 4 core ideas. Each agent gets a clear responsibility. You're a researcher agent, you're a writer, you're a viewer. So work is naturally divided. Agents can use APIs, databases, and external tools to work with real data. You decide how they collaborate, from simple pipelines to hierarchical teams, right? Do you want all the programmers in a room to have a discussion, or maybe that's too noisy and you just wanted to have individual conversations and then come back? And if you prefer, you can design and test workflows visually instead of writing code. I didn't do the UI, I'd rather write the code. Okay, so here, I defined exactly what he said. I have a researcher agent, an image finder, a writer, a layout, and then I gave it all of its tasks, and then I wired up the agents to their tasks. And this is what we got. So I actually asked it to write an article about Tikal. What's really nice also about Crew AI, other than the colors, is that it tells you, like, it's working on this agent, it's working on this task. You can really see what's going on. It's sort of like, I prefer Cursor because it tells me what it's doing, opposed to Claude's blurbing, fluttering, stupid little messages that it does. So here I like it too. Okay, so it took a while. It's up to the layout editor. And then it will create for me. I think it's still running, right? Yes, it reads me in HTML. And let's see what it gave us. Okay, it actually gave me an article about Tikal. Was pretty good. What's missing is the image. And all the agents that I've ever done, whether it's one for images or one for recipes, you always get stuck at getting the information. Like, if we could get past all of the you don't have permissions, if someone can solve that, everything would flow much faster. Crew AI brings order to agent chaos. Clear agents, clear tasks, real collaboration. Pydantic AI is a Python framework for production-ready Gen AI agents built by the creators of Pydantic. For some reason, Pydantic just sounds so much more professional to me than like Crew AI, which is fun. Moving from demo to production introduces 5 engineering problems. Consistent behavior is difficult when the same prompt can produce different answers. Free-form text has to be transformed into reliable application objects. Prompts become part of your application logic and require ongoing refinement. State management becomes an engineering challenge as applications grow. And supporting multiple providers means dealing with different APIs and behaviors. So Pydantic AI lets you apply the software engineering practices you already know to LLM applications. I wish we didn't throw away all the things we worked so hard on in programming, like clean code went out the door when Cursor can write you everything. But understand, agents are reading the language. If your code is clean, the agents will work better than if you have a million if-else statements that they can't understand either. Okay, so Pydantic said, I've done this before a million times, let me do it with agents. Responses become typed objects instead of text. Validation happens early instead of failing in production. Data and services are passed cleanly into your agents. Your application remains normal Python. And changing models doesn't mean rewriting your code. Okay, this weather assistant uses Pydantic models to define and validate agent-structured outputs, inject typed runtime context, and enforce that every LLM response conforms to the normal Python type definition. It's not going to be so exciting, but what you get to see is the classic Python objects. So you had to give it a name, and it says it could only get you the time in certain places. So in New York, London, Tokyo, and Paris. So what time is it in Paris? And when it returns its answer, it's going to be in a very structured way so that any other agent or any other section knows it. And also nice, tells you how many tokens you use, how many ins and outs, how many requests. Whether in New York, And then, what is the time in Japan? It's not on my list. So if it's not on my list, it says I can't retrieve it. Okay. Pydantic AI doesn't try to make LLMs smarter, it makes them behave like software. Okay, the last one, agency swarm. This was a guy who wanted to control everything. While running a consultant company that built AI solutions for clients, Arseny Shotkin set out to automate the agency itself by replacing much of his day-to-day work with coordinated AI agents. Agency swarm is built around 4 ideas. Every agent has a clearly defined role. Agents communicate through explicit messages instead of hidden prompts. Shared state keeps everyone working from the same context, and when one agent finishes, it deliberately hands the task to the next. Those 4 building blocks exist because multi-agent systems fail in very predictable ways. Once you introduce specialists, someone has to coordinate who does what. Without explicit communication, workflows quickly become fragile prompt chains. As workflows grow, agents need a shared understanding of what's been done and what comes next. Eventually, one agent becomes the bottleneck. Scaling means coordinating teams of specialists, not building a bigger agent. With agency swarm, coordination is part of the architecture. Okay, I thought it'd be cute and just give it an addition and subtraction, not even multiplication and division. I said there was a CEO, and the CEO's job was to divide a very long equation into, like, decide if the first part was 1 plus 2, then give it to the addition developer. And if it was 2 minus 3, give it to the subtraction developer. But it took it like 3 minutes, 2 minutes, 45 seconds. Yeah, so again, maybe the first 30 seconds was me. But just coordinating back and forth, like each piece had to go back to the CEO, had to back to them. Clearly, I chose the wrong framework for this situation. So again, it's 2 minutes and 45 seconds of it. Okay, so agency swarm doesn't build better agents, it builds better teams. As you can see, it's not about the best frameworks, it's about the right fit. If you want broad integration and quick prototyping, LangChain is a strong starting point. For deterministic workflows, LangGraph. For conversational multi-agent setups, AutoGen. For coordinated teams, Crew AI or Agency Swarm. And for production reliability and structured output, Pydantic AI. The right framework isn't the most popular, it's the one that fits your system. Okay.